Welcome back, everyone. So in this video, we're going to talk about resistance. Okay, now what is resistance? Well, the resistance is how well a wire or some other object, being a light bulb or something else like that, opposes current. Right, now, you need resistance, right? Some people might think, well, why do you need resistance? Why, what would be the point? Don't you want as much current as possible? Well, the answer is no, right? So the reason for that is it takes energy to move current, right? That's the whole idea of electric potential, right? You're changing the charge's energy, but not taking how much charge is actually there. So remember, it's V equals W over Q, right? Where V is that pressure to push the current through. Now, if you had no resistance, you'd effectively have unlimited current flowing through, right? Which is a continual buildup of energy. Now, that energy has to go somewhere when it's not being actively used by the circuit. So it gets radiated away as heat. Now, if you build up too much heat, what ends up happening is fires start, right? So it's very important that for a given circuit, you have the appropriate amount of resistance so you don't start fires, right? It's something that happens naturally regardless of what we try to do, but we can control how much resistance is in a circuit. That is another topic for another day. Today we're just going to mostly be talking about what resistance is and what factors of a wire specifically can affect that resistance. Okay, so let's start with those factors. There are four main factors that we need to take into account when discussing resistance. Okay, now the first one is this thing called resistivity. Okay, so resistivity. It's symbolized by this symbol here. This is called a rho, right? It's responsible for the Greek sound, right? It's basically their R, okay? Kind of looks like a fancy P if you were to type it out on Word or a Google Doc or something, okay? Now, resistivity is a material's ability to oppose current. Sorry, I'm just going to rewrite that, but make that a little better. Material's ability to oppose current, right? So it depends on what that material is made of. So an insulator, like a rubber or a plastic or something like that, will have a very high resistivity, right? It's very difficult for current to flow through it. Whereas a conductor, like silver or copper, will have very low resistivity because it's easier for that current to flow through, right? There's less resistance in a conductor, which is why it's easier for that current to flow through. Okay, now, the resistivity affects the resistance in this way. As the resistivity goes up, the resistance goes up. So this is your rho for resistivity, R is for resistance. Okay, so as the resistivity goes up, the resistance goes up. Think of resistivity as the material a road is made of. Okay, so a conductor would be similar to a nice smoothly paved road. Very easy for your car to drive down. A high resistivity would be a lot like a gravel road or a dirt road, right? Not as easy for that car to drive by. You got to be more careful. There's more bumps. It's going to end up slowing you down. Okay, now another factor that could affect resistance is the length, right? The length of the wire. Okay, and the way that affects it is as the length increases, the resistance increases. Right? Think about it like this. Let's say you're going down Main Street and you want to get to some food. There could be, let's say, some pizza places, right? The closer pizza place will be easier for you to get to, right? There's less traffic lights you're going to have to navigate. There's less pedestrians, less, stoplights or other cars, things like that, right? So a shorter trip will be easier for you to get through rather than a longer trip. So a longer trip, higher resistance. It's harder for that electron to go through the wire. In a wire, right, the electron will come across impurities or other electrons, so there's more things that can get in its way, similar to driving down a longer road. Okay? Now the next factor we're going to talk about is the area, more specifically the cross-sectional area. Right? So the cross-sectional area would be, if this is your wire, okay, the cross-sectional area would be the area of this circle, right? You cut it here, and then you just measure the area of that circle. So in other words, it's the width, it's the thickness of the wire. Okay? Now, for cross-sectional area, as the area goes up, the resistance actually goes down. All right? So in other words, for a wider wire, it's easier for those electrons to flow through. Again, let's think about a road. Right? It would be easier to drive down a road, any road really, if there were 2 lanes on either side of the yellow versus 1 lane on either side of the yellow. Right? So if someone's trying to make a left, you can legally scoot around on the right or whatever, and it's just easier to travel down. Right? For a wire, if the wire is wider, right, an electron can kind of scoot around other electrons easier, it can scoot around impurities easier, it's able to flow much easier. Okay. And finally, the last factor that affects the resistance of a wire is the temperature. Okay. Now, the temperature really affects the resistivity of the wire. Okay. So we say the temperature goes up, the resistance goes up. Okay, because what's happening is if you increase the temperature, you're increasing the resistivity, which means you're increasing the resistance. Okay, now let's think about why for a second. Okay, if you're in a wire or any kind of material, think about what you learned maybe in chemistry. As you increase the temperature, what's happening to the molecules? The molecules are going to start vibrating faster, which means the other electrons in the wire are going to start vibrating faster, and the other atoms in the wire are going to start vibrating faster. Right? So as you're an electron traveling through, you're going to be able to bump into those things more frequently. It's going to slow you down. It's going to make it harder for you to travel through. Right? For a road, for example, right? Not many people go outside when it's cold out. Right? So if you were to go outside, it's easy to just drive down the road. But when it's nice out, you got people coming over, they're going to go rock climbing, they're going to go, look at leaves, whatever, right? There's more people on the road, there's more traffic, it's going to be harder for you to travel through. Okay? So that's how temperature affects the resistance of a wire, and an analogy to go with that. Now, let's quickly talk about an equation. Okay? So we're going to take those factors, how they affect the resistance of the wire, and we should be able to figure out how that equation would look. Well, if resistivity goes up, and which causes resistance to go up, that means they're directly proportional, so that'll look like that. And then same thing with length, okay? So we have resistivity times length. And area, well, if area went up, the resistance went down, which means they're inversely proportional. Now, we're not going to have temperature in the equation because, again, temperature affects your resistivity, so that's kind of all worked in. So you end up with an equation that looks like this. Your resistance equals the resistivity times your length, all divided by the cross-sectional area. Okay, so there's your equation right there. Now, let's talk about units for a second. Okay. Well, the unit for resistivity is this right here. That's the unit for resistivity. This symbol here, that is called the ohm. Okay, it's actually the Greek letter omega, a capital omega, but we call it ohm after the scientist, right? Ohm, omega. Okay, so for resistivity, it's ohm times meter, so it's an ohm meter. Okay. For length, well, length is measured in meters. And area is measured in meters squared. Okay, so we have resistivity is ohms times meters, length is meters, area is meters squared. All right, let's put these all together and figure out what the unit for resistance will be. Well, we have R equals rho L over A, which leads to saying ohm meters times meters over meters squared. Okay, well, ohms times meters is ohms times meters squared, divided by meters squared. These cancel. And we're left with resistance being measured in ohms. So the unit for resistance is the ohm. Right? And that's pretty much all we need to know about this. On your reference tables, you'll find the resistivity at 20 degrees Celsius for a variety of different materials. Take a look at that when doing any practice problems, because usually they'll just put those in there unless they're asking you to specifically find a random resistivity. But beyond that, that's all there is to it, right? You have this resistivity, which is dependent on what it's made of, the material. You have the length, which just tells you how long the wire is. And then you have the cross-sectional area, which is a measure of how thick the wire is. Right? All these things kind of play in to create the resistance of a given piece of wire. Right? So that's pretty much it for that. We're going to move on and see how that goes from there. Have a good day.